Hey, welcome to The Explainer. Today, we're going to pull back the curtain on this tiny, microscopic process it's absolutely essential for the very device you're watching this on right now. We're talking about a journey into the world of ultimate, mind-blowing cleanliness.
It's a great question, right? Well, the answer is an insane level of cleanliness. I mean, it's almost unimaginable. Think about it. An environment where just one single invisible speck of dust could mean total disaster. Game over.
You see, for the super intricate circuits packed onto a modern chip, any little bit of stuff, any foreign particle, it's like dropping a giant boulder onto a tiny, perfect machine. It just messes everything up, short-circuiting the pathways and making the whole device totally useless. And that, right there, is the ultra-clean challenge that sits at the very heart of the semiconductor industry. So how in the world do engineers get this perfectly pure surface? Well, they use this legendary multi-step chemical bath called the RCA Clean. And get this, it was developed way back in the 1960s. So you're probably thinking, why are we still using something from the 60s? Well, it's because it is just so darn reliable and effective. It's the proven foundation that this entire, multi-trillion-dollar industry is built on. All right, so let's really dive into this procedure. This is a classic lab procedure, the kind of thing you'd see written down step by step. And believe it or not, this process, or, some version of it, is the absolute foundation of modern electronics manufacturing. So the first big hurdle? Getting rid of all that invisible gunk. We've got to strip away any organic stuff, oils from being handled, and then also any of these stubborn little metal particles that might have hitched a ride onto the surface. So first things first, we start by dissolving any of those organic residues. We're talking oils from human hands, maybe some machine lubricants. The silicon wafer gets a nice, hot 10-minute bath in acetone to do the job. After that, it gets a thorough rinse in what's called deionized water, and this stuff is seriously pure. All the mineral ions have been stripped out. That way, you're not accidentally adding new junk back on while you're trying to clean it. Pretty smart, right? Okay, organic stuff is gone. Next up, the metals. For this, we bring out the big guns, a super powerful mix of hydrogen peroxide and sulfuric acid. It's actually often called a piranha solution, which kind of tells you everything you need to know about how aggressive it is. This stuff is super corrosive, and its whole job is to chemically lift off any metal bits stuck to the wafer. And of course, that's followed by another really careful rinse. Okay, so this is the cool chemistry part. What's happening here is the two chemicals. They react together to create something called corrosive acid. And this stuff is an extremely powerful oxidizing agent. Basically, it just aggressively attacks and rips off those unwanted metal ions. It's chemical warfare on a microscopic scale. All right, now we get to the HF acid dip. And this next stage, well, it's probably the most critical and the most hazardous part of the whole shebang. This is where we get that raw silicon ready for its big debut. So the oils are gone, the metals are gone, but there's one last little barrier. You see, silicon is a bit like iron. When you expose it to air, it naturally forms this super thin layer of silicon dioxide. You can basically think of it as rust. And before we can build anything on that silicon, that rust layer, that native oxide, it has got to go. And how do we get rid of it? By dipping the wafer into a solution of hydrofluoric acid, or HF for short. The HF is like a magic key. It specifically targets only that silicon dioxide layer and just dissolves it away, leaving behind nothing but pure, perfect silicon. Now, this HF acid is some really special stuff. It is so reactive that it will literally eat its way through a normal glass beaker. I mean, think about that. That's why you absolutely have to handle it in special Teflon containers. And what's really cool is that it has this fascinating and totally visible effect on the wafer itself. Okay, so before the HF dip, the wafer is what we call hydrophilic. That just means water-loving. So, water spreads across its surface in a smooth, thin sheet. But after the dip, that pure silicon surface becomes hydrophobic. It actively repels water. So instead of sheeting out, the water beads up and just rolls right off. And that change, that switch from hydrophilic to hydrophobic, is the big visual cue. It's how you know for sure that the oxide layer is completely gone. Okay, so at this point we've done it. We have a perfectly clean silicon surface. But here's the catch. It's also super reactive now. So the wafer is pristine, but it needs one last little polish before it's ready for the big show, the next stage of manufacturing. So to finish up, it gets one last really thorough deionized water rinse. That's to make sure every last trace of that acid is neutralized and gone.
And then it gets a quick dip in ethanol. Why ethanol? Well, it's great at pushing away those last few stubborn water molecules. This helps the wafer dry perfectly without leaving any water spots behind. Because remember, even a tiny water spot could become a brand new contaminant and we'd be right back where we started.
And there you have it. It's like this incredibly precise chemical dance, right? And through it, a plain old silicon wafer is transformed into an atomically pristine surface. It's a journey from, well, contaminated to digitally ready. And honestly, it's this exact process that makes our entire modern digital world possible. It's kind of amazing.
So the big takeaway here really is the incredible lasting power of this fundamental process from the 60s. But it also gets you thinking, right? As we start building things on an even smaller scale, like quantum level stuff, what new kinds of clean are we going to have to invent? What's it going to take to prep the surfaces for the quantum computers of tomorrow?